So the next section that we are going to take a look at in this course is graph theory. So graph theory is a specific branch of mathematics that deals with connections of things. So it could be Facebook connections, like who your Facebook friends are. So all the different people that are connected and how they intersect with other people. It could be a road system, so cities, how they're connected by roads. This is a branch, like I said, called graph theory, that deals with kind of sometimes it's the efficiency of connecting things, sometimes it's getting things the most connected. So if you're talking about social media or phone lines or things like that, you're not necessarily looking for the most efficient way, but you're looking for the way to get the most people connected. So we have a lot of terms, a lot of definitions that we need to use in this section. They're not hard definitions, it's just terms you need to be familiar with so that you can understand what we're talking about. So when we talk about graph theory, we literally want to draw a picture of how things are connected, right? So we usually use dots to represent the things that are being connected. So if it's Facebook, it's the people. If it's a road system, it would be the cities. And then we use lines to connect those dots, and those we call edges. So we have vertices and we have edges. Vertices represent the things being connected. Edges represent the connections between the things. So they could, again, we don't really care how the lines are drawn. Sometimes you'll see them drawn straight. Sometimes you'll see them drawn with a curve. They can be short, they can be long. We don't care about the specific way it's drawn. We just care about the connection that is made between the vertices, which could be a city, it could be people, and the edges, which is the connection that represents, for cities, the edge would represent a road, right? For Facebook, the edge would represent two people being friends, right? Okay, so vertices and edges, that's what we mean. Let's see. And then once you have a picture drawn, once you have a graph made with these vertices and edges, we would call any route that you take a path. Pretty straightforward, right? So if you leave one city, city A, to get to city B, to get to city C, the specific roads that you take, the route that you take, would be called a path. And that is just the route between vertices, right? From one vertex to the other. So Euler is a pretty famous mathematician. He did a lot of amazing work in the 1700s, I believe. And he specifically did some work in graph theory. He was one of the first graph theorists. He was working on a problem of connecting locations across rivers, so bridges, right? If there were certain bridges that needed to be built or bridges that were already built, what was the most efficient way for travel to happen? So to look at what he determined, we want to define a few more terms. Like I said, there are a lot of terms. So path is just any way that you go from one vertex to another. But there are specific kinds of paths we can talk about. So if we talk about a closed path or a circuit, that was what Euler was specifically interested in. We would be talking about a path that begins and ends at the same vertex. So if you leave city A and want to visit 3 other cities but need to come back to city A, that would be a closed path or a circuit. An Euler circuit, which is what he was trying to create, is a specific circuit that actually hits every edge on the graph only once. So you leave from point A and you end up back at point A, but you have to cross every path that exists in the graph, right? So that would be an Euler circuit. You'll see that in your textbook. You'll be asked to look at Euler circuits. That's what it is. It starts at point A, ends back at point A, but it also hits every edge on the graph only once. So you can't repeat a line. You have to hit them once and only once. Okay. So that's what he was interested in identifying. Can we start at any vertex, move through each edge once, and return to that same vertex? That's the most efficient way to, say, pick up garbage, right? Garbage trucks in the city, is to hit every road, every house once and only once, and end back up where we need to end the day. He was able to definitively prove that that is only possible if every degree of the vertex is even. So what does degree of a vertex mean? Degree simply means the number of edges that intersect at that vertex. So if we're talking like our road and city analogy, then we're saying how many roads come into point A. If there are 3 roads that come into city A total, then that has an odd number. If there are 4, then it has an even number. So what Euler proved was you cannot have an Euler circuit. You cannot start at point A and end at point A and hit every edge only once unless every vertex has an even number of edges coming into it. So it's kind of helpful, right? Because you're not wasting your time trying to create an efficient path that doesn't exist. So that led him to his next idea of, well, what if we start and end at a different point, but we still want to hit every edge only once, right? If we think about our garbage truck analogy, then that means, okay, so maybe we could have our garbage truck start on one side of the city, hit every street they need to hit only once because that's most efficient and cost effective, saves gas, saves time, but we'll have them stop on the other side of the city. And then tomorrow reverse it, right? That could work. We have a different pickup and drop off location. So he did some work there, right? What would need to be the criteria for that Euler path? So Euler circuit starts and ends at the same place and hits every edge only once. Euler path starts and ends at different points, but still hits every edge only once. So what he proved there was that as long as you have exactly two vertices with odd degree, so 2 of them can have an odd number of roads coming in and out, but every other vertex has to have an even number, then it's possible, right? And those odd numbers would be your beginning and end point. So again, there are a lot of applications to these ideas. It just kind of helps planners, city planners, have a starting place, right, of what they need things to look like to be the most efficient. And you'll see a lot of those examples in your textbook and in your assignment that you're going to do this week. So hopefully that helps. Like I said, probably the most challenging part of this lesson, when you actually start looking at the graphs, it's very hands-on. It has pictures that are easy to follow, but it's making sure you get those definitions, you get the vocabulary down, like that you know what a vertex, an edge, a circuit, a path, knowing the difference between a circuit and a path. That will make all of it a lot clearer.